Hello, my name is Philip Sal. We met last year in Addis and Lawrence, if you recall, brought myself and Y over, and we also had Clemens Weber join us, who happened to be with the neurosurgeons. We're all spine surgeons. Y and myself are based in Leicester. I really enjoyed teaching you. I thought it might be helpful to have a little bit of basic pre-learning on biomaterials and bioengineering ahead of our teaching that we're doing in January. I really look forward to it, and I hope that you enjoy this little bit of teaching material. I'm not going to talk to every slide, but the important thing in considering biomaterials and bioengineering and the whole concepts is to consider the whole spinal construct. Often what we see from the industry is testing of a single individual item, and it's the whole construct that counts. This is a picture of the building of the bridge over the River Avon as being built by Isambard Brunel, one of the great engineers. You can see the various forces at work. On the suspension columns there's a compression force. The cables give a tension force, and there's also a reaction force within them. This is quite a busy slide. It simply shows the number of different approaches and devices and really procedures that we have available for spine surgery. There may be cements, emerging technologies, disc arthroplasty, but the mainstay of our spinal surgery are the pedicle screw and rod constructs that we use in reconstructing the spine or realigning the spine. It is quite clear that there's an overuse of implants in certain societies. You need to consider carefully what you're trying to achieve with your surgery and whether an implant is really needed. There's massive marketing goes on, and in fiscal-based healthcare systems there's an over-treatment and over-utilization of metalwork. Our basic principles would be that we need to reconstruct the spine if we have destabilized it. That is, in fracture work we might need to stabilize the spine. If we've done a large decompression, resection or debridement for tumour or TB, we may need to stabilize the spine and reconstruct it. In scoliosis work, we're obviously realigning the spine and then holding it in that corrected position while fusion occurs. There are certain places where we might use replacement technology, such as disc replacement. To be honest, that's fading now. More commonly, we might use cages or anterior fusion assist devices, particularly in the cervical spine. Implant failure occurs either because of use of an inadequate implant or because of excess loading and a failure of fusion to occur. There are many different biomaterials that we use in surgery. There may be biological materials such as heart valves. We most commonly use metal, particularly stainless steel and titanium, in trauma work and reconstruction. And in the spine, we'll sometimes use polymers, ceramics, or even composites. Biomaterials may be bioinert, bioactive, or they may be biodegradable. It's a fundamental fact that all implants will fail unless they're either of adequate bulk and size, and so a fusion is usually an essential part of any construct that we use. Quite often we'll use a integrating biological solution rather than a fusion external to the implant. Certainly the implant should outlast the patient, and that particularly applies in tumour work. So on to some basic biomechanics. You should be aware of the stress-strain curve. This is where a material undergoes an elastic deformation. It then yields and starts to plastically deform. At a certain elongation and narrowing, it will fail, and that's the ultimate tensile strength, or UTS. In the human body, there's cyclic loading occurs, and for that reason, materials are usually tested with what's called an SN curve. This involves multiple loading cycles, usually for metals at about 1/3 of the ultimate tensile stress. It's quite a long and laborious process carried out in the lab, but it indicates the cyclic life under load of some of our basic biomaterials. This stress-strain chart shows the different materials have different qualities. The flatter the line, the more ductile the material. So you can see here quite clearly that cobalt chrome under the same load doesn't deform as much as titanium. So cobalt chrome is the stiffer material and titanium is the more elastic material, with stainless steel somewhere in between. Young's modulus is how we quantify the stress-strain relationship and elasticity of materials. You can see here that cobalt chrome has almost twice the Young's modulus of titanium. The way materials fail is usually by crack nucleation. The first thing that happens is a small defect initiates the crack growth, and that crack propagates through the material until there's an ultimate ductile failure. There are many factors that affect the fatigue life of a material, and that's the load on them, the geometry of the structure, the rate of loading. Consider the surface finish of materials and the material type, and then also the way it's manufactured. If you think about how in the olden days people would make swords stronger, that would be by heating up the sword. They would plunge it into urine, and the urine with urea would nitrite the surface, giving a stronger sword. Many of the techniques that are used in strengthening our materials are well established within engineering. Here we have other factors. I'd like you to think about them. Think about them in the concept of cement techniques. The reason we use vacuum mixing is to try and remove gas pore voids within cement. Consider how we make concrete stronger. When you lay concrete for a garage floor, for example, you'll use shuttering to bring out the various voids and defects and produce a more uniform surface. Consider the environment. With temperature, consider how perhaps the process of sterilization might affect the material properties. Think carefully about each of these in turn. Mechanical failure can have catastrophic consequences in certain environments, particularly in the aircraft industry. These small aerial windows that were built into the Comet aeroplane were very square, and as a result they had stress risers. Under load, they produced a fatigue failure that was catastrophic for the aircraft. As you increase the diameter of a rod, you increase the strength of the rod, and rod strength increases to the radius of the fourth power. You can see how a simple increase in 1 millimeter in diameter produces a significant increase in the strength and bending stiffness of a rod, whether it's titanium, stainless steel, or cobalt chrome. So when you're bending a rod, you're aware of the increased forces required to contour a rod as the rod diameter increases. But also be aware that as you contour your rod, you're producing notches and little cracks in the rod that may predispose to fatigue failure. So the more precise and accurate your bending, the better for the ultimate strength of that rod. For a simple cylinder, there's a fairly simple equation. For more complex structures such as beams, we arrive at different equations. Here you can see the strength of the rod in relation to diameter. It would be good for you to consider the properties of screws. We use these frequently in general orthopedics, but more specifically in the spine, we tend to use them as pedicle screws or lateral mass screws. The major diameter is the outermost part of the pitch, and the thread length is the working strength part of the screw. In considering screw design, the shape of the pitch and the leading edge is quite important in bone failure. What happens in pull-out is that a cylinder of bone shears out. So the larger the diameter of that cylinder and the greater the cross-sectional or surface area of that cylinder is, the stronger the screw. So the greater your screw length and the greater the maximum diameter of the screw, the stronger it is in pull-out. For a material to be biocompatible, it needs to fulfill some criteria. And the simple criteria would be it should be non-allergenic, non-toxic, non-carcinogenic. There should be no toxic breakdown products, and certainly in spinal surgery we want it to be compatible with MRI scanning. An implant may fail as a result of different types of wear, fretting, corrosion, galvanic wear, and notching can all contribute to the initiation of a fatigue fracture and failure of the material. The human body is actually a very hostile environment. The main factors in screw failure and pull-out is the major diameter and the length of insertion of the screw. So you should carefully consider the screw trajectory that you're using to maximize the strength of that screw. Obviously, screws at the cranial and caudal part of a posterior construct have the greatest loading for pull-out. So positioning of the screw is quite important. The length of the screw is quite important, but probably the major feature for bone failure and screw failure is bone quality. There are techniques of screw insertion that will give a greater length of screw and therefore better biomechanical performance. However, there may be anatomical factors that limit the surgeon in their access to the best biomechanical performance. Consider the different screw trajectories given here. So I'd like you to look carefully at this rod and think about what sort of failure this is. If you look at the parts of the rod where it's failed, you can see the difference in the surface anatomy across about half the diameter of the rod. Why is that, do you think? It enables you, when you inspect an implant, to determine whether it's failed through never being strong enough in the first place, that is a catastrophic failure, or whether it's a fatigue failure and a small crack has propagated across the metal until it's ultimate tensile failure. As surgeons, we certainly need to consider the whole construct. We also need to consider the biology, the length of the lever arm, and consider all the risk factors when we're planning an implantation for reconstruction to try and avoid failure. I've covered some of the metals in quite detail because that's what we most commonly use, but you should also be aware of some of the biomechanical properties of ceramics, which we'll use sometimes, particularly in the cervical spine, as inserts into disc spaces following ACDFs. Ceramics, we can affect the porous properties by putting fibres into the ceramic and then burning the fibres out to give the porosity, and that porosity can be set so that it can be osteoinductive or osteoconductive. Polymers are in use. Some time back we used to use a flexible system called the Dionysus. It's definitely fallen out of favour now, and now there would be a combination of screws, polyurethane tubes and polyester cords or cables. Probably the most common composite we use now is PEEK, polyether ether ketone, and we use these as radiolucent cages quite commonly, but packed with bone graft so that the bone graft gives the long-term life of the implant. We use bone cement in orthopedics a lot and also in spinal surgery. If you're going to use a bone cement, you should be aware of its material properties. The cure time in particular can be very important. You also need to be aware of the additives. Sometimes it's slightly green as a result of adding chlorophyll. Sometimes there's antibiotics added to it. And the material properties can affect your ability to use the cement in certain environments. So bone cements that we use for vertebroplasty, for example, are commonly far more viscous and slower curing than some of the cements that we use elsewhere. Carefully consider all the risks of implant failure. If a patient has a loss of sagittal balance, the cervicothoracic junction will be forward of the ideal anatomical axis, and so the loads at that junctional zone between your implant are greater, increasing the risk of a proximal junctional kyphosis. Consider bone quality, osteoporosis, weight, and the actual implant that you're using. These are the key messages. If you want to read further, a really useful book is by J.E. Gordon. It's called The Science of New or Strong Materials, or Why You Don't Fall Through the Floor. It's essential reading for all engineering students, and I think anyone in the medical fraternity using implants should be aware of the key engineering message. I hope you've enjoyed this.